All right, well, let's get started. A little sparse today in class. So last time we left off with Hebbian Learning, and I'll revisit that, but I just want to provide a little bit more of a background context. And so in general, this sort of falls under the subject of learning from kind of a Psych 101 perspective here. So when we talk about learning, we have non-associative learning. And by learning, I mean here by kind of potentially permanent, I'll say changes. And for now, I'm going to just say in the brain. So focusing on the central nervous system. So there are other things that are learning like. So there's something called sensory adaptation. So if certain nerves receive a stimulus constantly over time, then they can tend to sort of filter it out. So there's filtering that can happen at the periphery, where you're sensing things. There's also things that can happen at the periphery where you're actuating. So you might like to be able to make a behavioral response, but you have so much muscle fatigue that it's impossible for you to actually make that response. And so it can give the appearance of a change in behavior when in reality, it's due to an actuation issue and not like a learning change. And so when we're focusing on learning, we're actually talking about things that are kind of being rewired in the loose sense in the brain, potentially permanently. So it's a plastic deformation in the brain. And there's two types of learning. We talk about non-associative learning, and this might include things like habituation and sensitization, the other kind of half of that. And so when we talk about habituation, these are sort of, this is, I would call non-associative learning, and these two sort of things is sort of like learning with relative to, learning involving only one stimulus. So I'm not talking about a stimulus being associated with another stimulus or another event. I'm just talking about, how you learn to respond to just a single stimulus. And so if you might habituate to a particular noise, and what that would mean is that you're constantly stimulated by that noise or by that image or something like that. So you recognize it, it reaches your brain, but your brain learns to ignore it. And so it doesn't raise a response. And so it's not because your sensory systems are filtering out, it's that your brain has habituated to it. The other side of that is sensitization, where you actually become hyper-focused on that. And so if there is one particular thing in your visual field or one particular thing that's it could be any sense, touch, for example, somebody touches you on your arm, if the stimulus keeps going and it's reinforced so that it becomes stronger and stronger and stronger to the point where it's really bothering you. So you can imagine there might be sometimes you're sitting in a classroom and there's a noise. So earlier in the semester, there was a noise coming out of one of the projectors. It just really got to me. And most of the days I might habituate to it. So it just becomes, I just don't even notice it's there. But that particular day, for some reason, it just became louder and louder and louder in my own head. To the point where I needed to make a change. I needed to investigate it. And so that's the example of sensitization. So you are learning, so you are changing the way that you respond to stimuli around you. That is learning, but you're not learning an association between stimuli and something else. It's more of a process of attention, of learning to pay attention to some things and ignore other things. So that's what we refer to as non-associative learning. And then there's associative learning. which involves a stimulus and another, stimulus, event, etc. So it is, it's two things that are relative to each other. And so when we talk about associative learning, very often things are broken down into two groups: classical conditioning and operant conditioning. So again, this is sort of basic Psych 101 stuff. And so when we talk about classical conditioning, this is stuff that is related to a researcher named Pavlov initially. And you've probably heard of Pavlov's dog, a dog that learns to salivate at the sound of a bell. When that dog originally would salivate at, say, the smell of food, but when the smell of food was always paired with a bell, initially there became an association between that bell and the smell, and the response that was associated with the smell then got imported to the bell as well. So a lot of times when we talk about classical conditioning, in the sense of Pavlov, people talk about the sort of conditioned stimulus and the unconditioned stimulus, as well as the conditioned response and the unconditioned response. And so the idea being there that before the learning task, before the conditioning, there was already a certain set of behaviors and associations that came as the baggage of the participant. And then through the conditioning, then you end up making new associations so that behaviors and responses that were already present with certain stimuli get associated with others. And so this idea of generating a conditioned response, this is sort of what relates to what we refer to as unsupervised learning. So the idea being that there's no additional reward being made. We're not trying to convince the animal or the machine to do something that it has never done before. We're convincing it to make an association between two things. And in conditioned classical conditioning, in the laboratory, you specifically you kind of know what the things are there. But in kind of unsupervised learning, there is an assumption that the data that you provide to the machine is going to have certain things that are going to be related, and it's naturally going to find those relationships. The same way a dog naturally starts realizing that there's a bell that's always associated with the smell of food. And once the brain makes that connection, then the dog just can't help it. Its mouth will start to water when it hears the bell, even when it's not partnered with the smell of the food. So that's what we refer to as classical conditioning, which I'm going to draw kind of a line towards sort of related to unsupervised learning. And then on the other side of associative learning, we have operant conditioning, which is associated with a researcher named Skinner. And Skinner came after Pavlov, and operant conditioning was supposed to be a way to sort of dial up the studies of learning to be like more useful somehow. And so he said, well, we're not just going to try to find associations we're not trying to just form associations between stimuli. What we actually want to do is try to use reinforcement or punishment to encourage certain behaviors over others. And so we're actually trying to change the distribution of an animal's behavior. So I'll say this is like association between, I'll say behaviors and reinforcement slash punishment to change the distribution of behaviors. So this I'm relating to like supervised learning or reinforcement learning sort of fall into this camp. Where the goal here is through an assay or through a conditioning process, you get an animal or a machine to generate consistent behavioral outputs for consistent inputs that you provide. So in the case of an animal, you might say you can go left or you can go right. And if you go left, you have no idea initially whether you go, whether left is good or right is good. And so the animal just randomly decides to go left or right. So it makes certain behaviors, but occasionally it finds that when it goes left, it actually gets a reward. And when it goes right, it may not get a reward or it gets punishment. And so over time, it may learn to associate left with reward. And so this often involves in the brain, there is a reward circuit, or there are reward circuits. And I'll just mention, and this is kind of just background information, it's not super important here. Dopamine is one of the things that I could, so there's dopamine generating neurons, dopaminergic. Sorry, this is one of the, yeah, dopaminergic, that's the, and so basically in your brain, there are a handful of neurons, not that many of them, that can produce the neurotransmitter dopamine. Now, we've already talked about neurotransmitters. They're the chemicals that in synapses actually go from one neuron to another. And so there's a couple of these, there's these reward centers in your brain. And when you get rewarded, these reward centers have these long axons that go into all sorts of other parts of your brain. And they can generate dopamine. And dopamine is, again, it's a neurotransmitter, so it can generate a little bit of a synaptic potential at other neurons all over your brain. So what ends up happening here is when you get rewarded after you've done a behavior, then you get this internal synaptic potential that causes some of your neurons to fire more easily than they would if they didn't receive that reward. And so what ends up happening is these processes of Hebbian learning, for example, that I'm about to go back into, they end up forming an association between whatever you just did, that behavior, and it basically ends up strengthening. And so let's say, you see a stimulus, something, blue color, blue or left or something like that. You see something where you look and you know that direction's left and that direction's right. And that stimulus, then you end up happening to decide to go left when you see that left is an option. Well, if you've got this reward center, then it's going to strengthen that association so that when you see left, you're going to want to go left. And so it provides sort of an extra bias for spontaneously associating these certain stimuli with particular responses. And so it's a feedback center in your brain that ends up generating strengthening of these weights. So that's kind of what we do in operant conditioning. You're kind of dialing into that, whereas in classical conditioning, you're not necessarily, it doesn't have to be a reward. There's just already an existing pattern there where you have a stimulus and it produces a response. And so if you happen to also present other stimuli along with it, your brain will naturally start to now associate those new stimuli with the old stimuli and eventually start producing the response that it would for the old stimuli for the new stimuli too. And so there's no extra reward in the classical conditioning. In operant conditioning, you're actually engaging the brain's reward center to reshape those connections in a way that could be somewhat arbitrary. So you're training the brain. So the emphasis on training is why I associate operant conditioning with supervised learning and reinforcement learning. The emphasis on lack of training is why I associate classical conditioning with unsupervised learning. But my point here is that if you have a mechanism for associative learning, in principle, you can actually do all of the learning styles that we've talked about here. So whereas when we think about machine learning and artificial intelligence, we have a very different way that we set up our algorithms to do unsupervised learning, supervised learning, and reinforcement learning. But in theory, behind them all, you could build a sort of biologically plausible associative learning mechanism, and you could treat a machine like an animal in the laboratory, where you could sometimes be giving that machine reward. So you need some sort of reward circuit in the machine's brain, but you could also sometimes, not give it reward. And you could, through the design of your experiment, the design of your data set, then sometimes you would get unsupervised learning that would come out of that, and sometimes you get supervised learning or reinforcement learning that would come out of that. It would just happen naturally with that. But that's not necessarily super efficient. But that's one of the reasons why there is an interest in thinking about associative learning more broadly, because it really is foundational for all of the learning that we hope that artificial intelligence can do to mimic what we can do. So that's kind of a quick background of learning in general. Any questions about that? I didn't turn the online chat toward me, so I don't think I see any extra icons there. Any questions? Yeah.
You say like the genetic algorithm, like what we did at the beginning, is that you rank based on their fitness, based on how they did, and the ones that did good kind of had like more children, which is what they want to do, I guess.
Okay, so there's a question sort of mixing metaphors here where we're saying the question was, we learned about the GA, and the GA basically selected for certain individuals that outperformed other individuals. And so could we kind of view that as sort of an operant conditioning where we're kind of providing a reward that reshapes the distribution of outcomes there? And certainly the outcome of such a process is similar. The inspiration, the mechanisms behind it all, I think are qualitatively different, because some people talk about evolutionary learning. So we're saying that, like, let's say the environment cools down 10 degrees, over the entire planet. Well, that is going to put a huge selective pressure on the populations of the planet, so that you're going to get a totally new distribution of organisms that some are going to be better adapted for that 10-degree cooler or 10-degree warmer weather, and others, that weren't, will sort of drift away. So if you view the planet as sort of a learning machine, then we can say that the planet has learned how to respond to this new temperature stimulus or something like that. But that's kind of that's just sort of a narrative. It's an interesting sort of story on top of that. We say, how useful is it to think about the planet as a learner or evolutionary learning? So they're certainly related. The outcomes are related, where we get a different distribution of outcomes that due to a reinforcement. But here we're sort of appealing to mechanisms that are not evolutionary. They're developmental. They're life history stage. So I think it's a great thought, and you should keep that thought, because a lot of times, especially when we're building multi-agent systems, we often build multi-agent systems where each individual learns during its lifetime, but then we change the distribution of individuals in the team over longer timescales. And both of these processes then apply. So, for example, even the ability to learn, that's something that, sometimes you don't need. It's like, there's a bunch of things. It's actually much cheaper for a biological organism to do something that it doesn't have to learn. It's just great to just pop out of the womb or the egg or wherever and immediately know how to do things. And whenever that's possible, that's probably better, unless you're in an environment that's changing very frequently. And what's interesting is, in human situations, most of the things we learn is actually pretty costly. Like there are alternatives that we could have done that don't involve learning, but we think that the reason we learn is because we're in a context of learners. So the fact that we have to live in a society of other people who can learn how to behave differently means that we have to learn how to respond to their behavioral differences. So the fact that you have 8 billion learners out there means that each learner, the reason each learner is a learner probably has less to do with variable environment from like, biology or whatever. It really has to do with the fact that, if I get screwed over when I'm 6 years old, I'm going to remember that. I'm not going to get screwed over when I'm 16 with the same trick. So the fact that people can learn creates an environmental shift that actually puts a selective pressure that makes it beneficial to learn. And so it's this like runaway process where part of the reason we think we have big brains is not because we needed them to deal with the environment. We needed them to deal with other humans that had slightly bigger brains than the humans that came before. So, so all of this stuff is great to think about, but it's really kind of more of a, at this point, like a think about it the pub type of thing. It isn't something we can easily operationalize in the lab, but people are working toward that, where we talk about evolutionary learning as well as life history learning, but it's something that is not quite hashed out perfectly. Does that kind of get at all the answers? Okay. All right, any other questions about our general outline here of learning before we go back to Hebbian learning? Okay, great. All right, so that's the reason why, one of the reasons why associative, I mean, again, normally when we think about associative learning in terms of artificial intelligence, we're often thinking about unsupervised learning because it's kind of a direct mechanism for that. But in principle, you can take unsupervised learning and add in a reward circuit and end up turning the same mechanisms that do undersupervised learning into supervised learning. But we just have kind of more direct ways to do that with things like backpropagation and so on. So it's a little more efficient for us to use those methods than to sort of wait for our machine to figure out that it's getting a reward. And it's just a little slower to learn this way. But in principle, this is very fundamental, this idea of associative learning. It kind of can do it all. So if we want to do unsupervised learning, what are mechanisms that we can mimic? And so one, tool for associative learning so an associative learning mechanism in the brain is STDP, or spike timing dependent plasticity. And this general topic of spike timing dependent plasticity is what neurophysiologists will look at a neuron and will say, what's the probability of the synaptic sensitivities of this synapse due to some presynaptic neuron or postsynaptic neuron? So either changes in receptors or changes in how much neurotransmitter is being produced. What's the probability of this synapse getting stronger or weaker based on the timing of an action potential in the presynaptic neuron or the postsynaptic neuron? So in general, it's looking at timing of action potentials, of nearby action potentials. So I'll say this, how does timing of nearby action potentials change synaptic sensitivities? And one model of that is so-called Hebbian learning. Where in Hebbian learning, the idea, so just as a reminder, if I were to draw, a neuron with a long axon, and then some other neuron with its own axon. And this neuron's got other axons from other neurons that are coming in. So this is the axon, and we're going to focus on this synapse. And we refer to this as the presynaptic neuron, and this is the postsynaptic. And so there's going to be an action potential that travels down this neuron, and there's another action potential that travels down this neuron. And we're interested in the relative timing of these two action potentials. Timing of nearby action potentials. All right, so in Hebbian learning, this is the idea that, and this is summarized by those who fire together, wire together, which is a simplification of a quote that people other than Hebb made about Hebbian learning that was a slightly different quote, which I talked about last time. None of that really matters. Everybody just says this quote here, those who fire together wire together. And the idea here is that if you get nearby action potentials in A and B, so A has an action potential and a B has an action potential, and they're very close in time together, and sort of the chemical time scale is very close together, then if A fires just before B, then we want to increase, or the synaptic connection is enhanced. But then it also goes the other way. If A fires just after B, then the synaptic connection is reduced or decreased. And that's Hebbian learning. So the idea here is in the brain, you got these two neurons, one neuron fires, and remember that this other neuron, this B, it's got other axons that are coming down and interacting with it. And so it's got maybe another neuron C, D, E. And so B has got a lot of things stimulating it. A is just one of the things stimulating it. The action potential that's coming down from A, that might not be enough alone to generate an action potential. It generates a synaptic potential, but that synaptic potential might not be enough to cause B to go across it, to cut its threshold and generate its own action potential. So there's other signals coming in from C, from D, and from E, and those sum together with the signal from A, and that generates an action potential in B. If B's action potential happens to be generated slightly after A, then Hebbian learning kind of captures the idea that there's probably some kind of causal link, that if A fires, then it's probably a good idea for B to fire soon after that. And so if this pattern holds, that for whatever reason B fired, it might have been because the connections to E, D, and C were really strong. If B fired just after A fired, then the connection to A is going to get stronger. And this is going to happen over and over again. If this timing pattern frequently occurs, this synaptic potential is going to get stronger and stronger and stronger, to the point where if A fires, B might fire even if C, D, and E didn't generate a synaptic potential. So it just reinforces these synaptic weights based on timing characterizations here. And you can imagine how this might, this might be a mechanism that explains things like Pavlov's dog. You've got sort of this, this neuron that ultimately controls the salivary response, and it happens to, and there's a neuron coming down from it. So this is maybe a neuron that's related to the smell of food. And this is maybe a neuron that relates to the bell sound. Now, normally the bell sound isn't enough to generate the salivary response, but the smell is. So if you externally always pair the smell with the bell, then what's going to happen is that the smell and the bell are going to arrive to B first, and then B is going to then trigger the salivary response. Now, that may enhance its connection to the smell, but it's already pretty high. But it's definitely going to also enhance its connection to the bell. And so as this connection gets more and more enhanced, it might become so strong that actually the bell alone will be enough to trigger the salivary response, even without the smell coming in. So that's the idea, is that Hebbian learning provides a mechanism that, between these neurons allows them to dial up and dial down these synaptic connections. Does that make sense? This idea of, now remember, there's all sorts of other ways you could propose that timing would affect synaptic modulation or synaptic modification. And that kind of falls generally under spike time dependent plasticity. But one particular type of that is Hebbian learning. And that's the one where if A comes first, then the synaptic connection gets increased. If A, but the other way around is also true. If B comes first, then we don't actually want this connection to increase, because that might create some weird positive feedback. Because if B is coming before A, that suggests that there's some connection where when B fires, eventually A is going to fire. And maybe we actually then don't want to just create this reinforcing feedback loop. So if B is firing before A, then maybe we actually reduce this synapse. So that's Hebbian learning. So questions about that? Does that make sense? That's in the spiking case, how we implement Hebbian learning. Okay, so just a review of what we talked about last time. All right, so we can mimic that with an artificial neural network. And the idea here, and maybe I'll just put that on a new page. So the Hebbian learning in ANNs, and this is mainly for unsupervised learning. Now remember, the ANNs we've talked about so far are not spiking. So we have to sort of turn spike timing into something else. So, we instead, okay, the picture here, I guess I'll draw that out. So the same idea, my two neurons here, I've got this neuron here, which I'll call A to match the previous picture. And another neuron here we'll call B. The state of A, I'll call X of A, whether A is currently triggered or not. The state of B, I'll call X of B. There is a weight in between them. Which I'll call W, A, B. But there could be additional neuron inputs into A that cause it to fire. If we want to use that term fire, it's the weighted combination of its inputs. And then there's also other inputs into B that are going to be summed together to determine whether it generates an output. So same sort of picture, but now these are our standard neurons with activation functions and so on and so forth. And so spike timing dependent plasticity, is analogous to a weight update formula where we say the weight in the next time step is equal to the weight in the previous time step plus, and I'll just say some function. And in general, this can be a function of the state of the whole neural network you know, or I could say specifically just XA of K and XB of K. So generically, this update rule in principle could be gradient descent. So you can come up with an update rule that fits this form. And if you really think about it, this is gradient descent. You know, I've got weights here, and then I've got a function, and that function could just be, you know, say if the gradient is known. So if I know if I have some loss function that I can use to generate a gradient with respect to this weight. Oh, and I'm sorry, this should be WAB. I apologize for not writing that down. I'll clean that up a little bit here to make that clear. All right, so in principle, this could be gradient descent. You know, it's just an update rule where if you know the gradient, you plug in all of the states of all of the neurons right now, you could get the gradient, you know, partial E with respect to partial, you know, like this could be partial E with respect to partial WAB. And if I knew that gradient, I could plug in the expression for that gradient here, create a descent step, and so on and so forth. So this is a very general framework here, but I could come up with other update rules that also fit into this. And so for Hebbian learning, we choose the form where WAB at K plus 1 is equal to WAB at K plus, kind of borrowing from gradient descent, some learning rate but then instead of putting in a formal gradient, I'm just going to put the states XA at time K times XB at time K. And these states, I'll say XA and XB, imagine they have activation functions where, for example, they could be distributed from, you know, -1 to 1. So we've chosen, you know, say activation functions. So in this case, what firing before and after has to do is whether you're mutually high, mutually low, or differ in your activation. So if they both agree in sign, then the weight between them, so I guess I could write that here, is agree in sign implies increase weight, and then disagree is decrease weight. And you can, again, come up with other STPDs. So like for example, there's also what's known as anti-Hebbian learning. And anti-Hebbian learning looks identical, but this plus is a minus, where it would basically swap these two things, where if they agree in sign, you decrease, if they disagree, you increase. So there's all sorts of different rules, but this is generally the Hebbian learning rule. Now, if you think through this, there's potential problems with this rule. So for example, the weights could run away. So let's say they agree, A and B agree, then the weight between them is going to increase, which is going to make it even more likely that when A is a 1, that B will be a 1. When A is triggered above threshold, then B will be above triggered threshold. And so this increased weight will increase even more. So these weights can run away to infinity. And so there are modifications to this that prevent the weights from running away. So, you know, I could say advanced topic, modify to prevent runaway. So that can be done, but it's kind of outside of the scope of this class. I just want you to get in this basic idea that this is an update rule, not that different from gradient descent, where instead of using the gradients, we're just using the states of these adjacent neurons. And when the neurons agree, the weights increase. When they disagree, they decrease. And you run this over and over and over again, and gradually your weights converge on some particular weights for the particular input that you're giving them. I see a question online. Can Hebbian learning effectively be modeled as a Markov decision process where the weighted paths are a function of frequency, of action potentials, and timing? I think that, so when we talk about a Markov decision process, I mentioned that reinforcement learning, for example, can be modeled as a Markov decision process because we explicitly have states and rewards, and we move through states based on the information we get based on rewards. And then I also mentioned that you can use associative learning to implement reinforcement learning. So definitely I think that you could probably come up with a nice narrative or a nice structure where you could talk about STDP or Hebbian learning in this context. You might need to add in external feedbacks, as in reinforcement learning. But certainly, I mean, whenever you start seeing states, like if we think about this as a continuous state and how does it evolve, then certainly this is a Markov process for sure, right? The next state depends on the previous state and only the previous state. And here we haven't even really talked about the external inputs, but they eventually come into play here. So, so I definitely think you probably could tug at that thread and it would eventually lead you somewhere. I don't have a direct answer to where exactly it will lead you, but absolutely this could be related to that type of modeling perspective. Okay. So any other questions about this? This is our kind of ANN implementation of STDP or Hebbian learning. All right, so what does that get us? What can we do by having our neural network be wired up this way instead of giving it a bunch of data sets and then having you do like back propagation and all that? So this is particularly good. So we have unsupervised learning is particularly good at pattern identification and to some extent classification. And you can relate this to Pavlov's dog, recognizing that there is a pattern. Whenever I smell an odor, I also hear a bell. And it gradually learns to associate the two of those together. So there was an output that corresponded just with bell. And over time, that output then corresponds to bell and, I'm sorry, the output corresponds to just to the smell. And then over time, the output corresponds to smell or bell. And so that's kind of an example of what we mean by pattern formation. A more concrete way to apply that to machine learning. So sure that some of you are maybe familiar with like, these test data sets like the MNIST data set or the FashionNNIST data set and so on. And these are data sets where they're basically little bitmaps of items that have classes that are definitely recognizable to humans. So for example, this is MNIST is, let's say a bunch of numbers in bitmap form. FashionNNIST is a bunch of things like shirts and shoes and etc. And so you can train a neural network on these things. So you can give them a subset of those things and say, these are all the ones, or all of these things are one, all these things are two, all these things are three. And after you've trained it with supervised learning, say doing back propagation, then you can then validate and test it on other slices of that data set. So here's some ones that you haven't seen before. Do you properly classify them as a one? Here's shoes you haven't seen before. Do you properly classify them as a shoe? And so on. Now, what you can do is you can actually present similar sorts of inputs. So let's say I'll do a little grid here. So in my notes, I have a 5x5 grid, but but I don't exactly. Okay, I'll do this. So let's say I'm considering two different images. And this image falls under the U category, and this image falls under the A category. And what I mean by that is, imagine these are pixels, they're either on or off. And so in the U category here, I'm just going to count over here to make sure I give myself enough room. So these are my pixels. They're in my little diagram, they're 3x3 blocks. And so imagine if, I'm just going to go ahead so I make sure that, make it clear. So a little 5x5 square in both cases here. All right, so a potential U might have these set of pixels on and everything else off. And a potential A might have these set of pixels on and everything else off. And so this kind of looks like a U, this kind of looks like an A. Maybe I should have done ASU instead of UA, but you get the idea. And so you could then imagine running these into an artificial neural network. And that network has got multiple outputs. Let's say it's got, I don't know, 8-bit output or something like that. So it has some output here that's got 8 bits, I think. And so imagine initially choose random weights. So if I choose random weights, then if I pipe in a U into this neural network, just randomly, there are going to be certain neurons that are more likely to agree in their activation. So, the like if I'm thinking about these output neurons here, for example, or even neurons in the hidden layer, going from hidden layer to output. The idea here is that, like randomly speaking, there's going to be certain patterns that are more likely to produce certain patterns on the output here. Let's say if there's 8 outputs here, there are just certain patterns that will naturally have, maybe produce a 1 out here just automatically. And other patterns that'll maybe put a 1 in a different spot automatically. And so the idea here is that if I keep passing in inputs that cause those outputs to fire, then the Hebbian learning, I'll say then use Hebbian learning, then outputs that correspond to patterns that are constantly being hammered on this neural network we'll have the corresponding weights that were generating those outputs increased, and weights that that are sort of connections that are unrelated to that firing decrease. And so there might have been, initially when it was totally random, it was very likely for the U to light up this bit, and it was maybe less likely for the U to, didn't quite reach activation for this one. Well, over time, this one will always be lit up when the U is hit, and this one will never. The output that we see before its activation function will end up getting lower and lower and lower. So the idea here is there's going to be some background associations that are just randomly going to be present in this randomly initialized neural network. And Hebbian learning, those patterns that were just sort of start kind of being detected at random, because they keep getting reinforced by, I don't want to use the word reinforced, because the neural network keeps seeing them, then the weights corresponding to the pathway from this pattern to an output are going to continually get reinforced by Hebbian learning. And patterns that it has never seen, and if I would have never shown it an X pattern here, initially, if I showed it an X, there might be some probability that I'm going to get a little bit of activation for this output node down here. But if I never show it an X and it goes through this whole process, then it has no reason for that output to ever get reinforced. And it might start effectively ignoring X's because it's never seen them before. So over time, what you end up getting is a pattern on the outputs. So this is just for this example. And I'm just gonna, this is just random, the string I'm gonna hear. You might say that whenever you show it U's, then you get maybe these 3 bits turn on. But whenever you show it A's, then maybe these 4 bits. So, and those are meant to be the same, turn on. And so what ends up happening is you get an emergence of a code for each class of digit or letter. So this unsupervised learning, you can view it as it's doing clustering, it's clustering letters together that are very similar. That's one way to view it. You could view it as maybe doing anomaly detection. There's a bunch of different ways you can make use of this, but it's effectively become a classifier without any supervision. Just because it sees a lot of U's, it ends up generating a code which we can then train. Like we can use this as a low dimensional version of everything that comes out of here. And we can learn that whenever we presented any sort of U, these 3 bits show up. So that is now the code for U. So we can take very high density data and boil them down autoencoder-like into a low density thing. And that mapping happened automatically. Now, because it happened automatically, we can't enforce whatever code that we want here. Like in a supervised learning situation, I might want to do like a 1-hot encoding where if I've got 8 outputs here, if you show me a 1, I want it to always be this output. If you show me a 2, I want it to always be this output. Show me a 3, always this output. Now in supervised learning, I could enforce that by providing a reward function. But for unsupervised learning, I'm not providing any reward for what the output looks like, but it's just naturally noticing that it sees a lot of inputs that look like U and a lot of inputs that look like A, and it reinforces weights that are tickled simultaneously by the U and reinforces weights that are tickled simultaneously by the A. And that's what generates these consistent patterns on the output whenever you then show it U's and A's. So that's kind of an example of pattern identification or clustering or classification done without reward, totally by a Hebbian update rule, unsupervised learning. All right, so any questions about that? Okay. All right, so that's what we can do with conventional artificial neural networks. But these aren't spiking, and I mentioned this is all inspired by spiking. So, so the thing here we could say is, what about truly spiking neural networks? Or SNN. So we've been forcing these analogies between spiking and threshold functions and all that. And then so the question that it's natural to ask is, can we go further and actually build neurons that act like real neurons? And what do we get out of that? And this sort of follows a natural evolution. So the first neural networks, I'll say neural network first generation, you know, it was kind of the conceptual model where we didn't consider a lot of different activation functions. We just sort of thought of the activations as being kind of binary. So, you know, on, off. And we sort of viewed this as inspired by neurons, because we often think of neurons as they're spiking or not. You know, there's an activation potential or not. And so this is kind of, you know, sort of bio-inspired. And but then people realized that, you know, we could generalize that. And you got kind of the second generation of neural networks where you trickled in a bunch of these other activation functions. So now we have other continuous activation functions. And that allows us to do other things with neural networks like linear regression and so on. This gives us a lot more flexibility. You might think of it as maybe getting farther away from the biology because, but that's kind of, I think, unfair, because in reality, it just so, I mean, as we're getting into the third generation here, biology tends to do its computing where it encodes things temporally. And this is really just saying, we're going to take the high resolution encoding that we see in biology, and we're just going to encode them spatially. So we're not going to encode things as a pulse, where it's a high density pulse or a low density pulse, as we're about to see. We're going to take another direction. For simplicity, we're going to say that if something is spiking a lot, then it's the input is got a high value. If it's spiking little, the input's got a low value. So I wouldn't say it's actually getting farther away from real biological neurons. It's just encoding these activity levels as single variables, as opposed to patterns that are changing over time. And then that finally got to sort of, you know, what we got now, the third generation of, you know, neuromorphic spiking neurons, where we actually stop thinking about each neuron encoding a value in as a variable. Like, we don't think about the output of a neuron at an instant. We think about the output of a neuron as a pulse train over time. And so if we were to take a small time slice, how often is this neuron on? How often is this neuron off? That's really now what's encoding value. And that's what I'll start to elaborate here now. And so this, I think a lot of people associate this direction with somebody named Carver Mead. So kind of neuromorphic engineering is associated with Carver Mead. I think in like sort of the 1980s. And this was almost more of an artificial life type interest. Like Mead would look at things like the eyeball and would say, like, there's a lot of really cool stuff going on as images hit the retina, and those then get turned into signals that are processed downstream in the brain. Let's actually build neurons that mimic that entire process. And he managed to build these artificial systems where they would, you know, you could could take these little neuromorphic cameras and aim them around the room, and it would end up producing images on the screen, but all of the information processing was done through this spiking. And so there's a lot of analog electronics that were involved in this. And so as more light hit some of these elements, they caused them to spike more. As they spiked more, they tended to cause other neurons to spike more. You could do computing that way. And then you could end up actually doing kind of basic computer vision, but through this sort of weird mixture of analog electronics that was mimicking what's going on in the brain. And so the focus here was on a higher fidelity model of real neuronal dynamics. So rather than being this simplistic model where things are either on or off, then they really wanted to get into, again, the analog side of this, of like, how does a neuron develop an action potential over time? You know, how easy is it for that action for it to lose sensitivity temporarily and then regain its sensitivity, and so on. And so because of this higher fidelity, it involved a lot more analog electronics, for one, and simulation as well. And so oftentimes we'd say like, well, we don't have the hardware device that can mimic this neuron. So what we're going to do is in silico, in simulation, we're going to build a simulated neuron that behaves over time like a real neuron. And we're going to put a bunch of those together and see what sort of computing systems we can build in simulation, as if we had them in real life. And then maybe someday we'll have them in real life, and then we'll be able to see where they go from there. And the hope was that, and so this is back in the 80s, so people aren't as worried about energy and things like that the way they are today, but that will come into this in a second. But the hope was that large numbers of realistic neural elements combined in high density might be the key to finally emulating the human brain. So you have to remember, think about the 80s are coming out, neural networks are sort of very basic, computing is still very limited, and people say there's something missing in the way we're doing computing. And without really knowing all of the theory behind it, the thought was, well, let's just plow on forward trying to build neuromorphic hardware that's as close to the hardware up here as possible. And once we start building systems that structurally, mechanistically look more like the system that's inside here, then we'll finally be able to do the experiments to really maybe better understand what's going on here, and finally maybe be able to achieve the levels of sensory abilities and computation that's going on inside the brain that really seemed way out of reach in like early 1980s hardware. So that was kind of the motivation here. It wasn't driven by energetic concerns or whatever. It's just this idea that computing was boring and information processing in natural systems was exciting. So in order for us to go from boring to exciting, maybe the step to that was mimicking what's going on in the real brain. And maybe we'll discover a lot of other useful properties and so on and so forth. So, and I've already sort of talked a lot about the spiking neuron and things like that. I guess I can quickly review that, or maybe I can sort of, in the last couple of minutes here, decide what to trickle in now and what to talk about next time. Nowadays, I guess I might mention that maybe that's a good way to go with this. Modern SNN, there are, maybe I'll put this on the next page here. And you could say, cut to today. modern SNNs. And our modern spiking neural networks largely sort of fill out some of this vision of, what this hardware should look like. So we now have hardware devices that mimic the analog profile, activation profile of real neurons. And so basically these are, some of them capitalize on analog elements, but increasingly what is happening is you're seeing more and more of these hardware platforms, and I'll mention a couple of popular ones here from companies you may have heard of, that that are saying, but we now are so good at digital, high-speed digital, that we can actually compress we can build application-specific integrated circuits, digital circuits that provide us the flexibility to mimic these, effectively simulate in hardware any neuron profile that we want. And so now we've got digital emulations of analog models, I'll say math models of neuronal activation. So the way these things work is they basically give you a grid of spiking neurons I'll say digital spiking neurons. And you can program them by saying, I want these neurons to have this particular ordinary differential equation model of spiking with this particular connection profile. So this allows you to say, like, well, there's this model of activation, this Hodgkin-Huxley model of activation. We're going to use that. But then you can say, well, actually, there's now been more refined versions that are more sensitive to some things, or maybe they last longer, or the spike, looks as a different shape. And so we can download that instead. So now you can actually program the sort of analog properties of each individual neuron and then wire these neurons up together. And so the platforms that are out there, the kind of big ones here, the first kind of popular one was an architecture called SpiNNaker. So notice the capital S, capital N. And in SpiNNaker, this was a supercomputer architecture where instead of building very, very small neurons, the idea was we're going to use our high-powered computers to emulate this sort of setup here, so that we could then get sort of move on to understanding SNN architectures. But now we're actually seeing these small-scale hardware implementations, like IBM has its TrueNorth, and Intel has Loihi. And these here are small scale, high density hardware implementations of spiking neuron profiles. And so there's a chip. You could buy a Loihi chip where on something that you can actually is small enough that you can put onto a quad rotor, you can actually then have it implement a spiking neural network that takes inputs from the outside, from standard electronic sensors, and produces outputs that go out to motors. And all of the information processing is done in a spiking architecture inside Loihi. So you got, and I don't know what the current density is for these number of neurons, but I mean, we're talking about like, we're starting to get to significant numbers of neurons in high density and small packages that are very lightweight. And these tend to be very low energy. The challenge here is knowing how to make use of these spiking neural networks and having enough spiking neurons to do something really, interesting and useful. But the promise here is because they only have to be on while they're spiking, they don't actually use a lot of energy while they're just sort of sitting there. And so the thought is that maybe one of the outputs that's going to come out of using spiking neural networks to go beyond just getting higher biological fidelity is actually getting closer to implementing the very low energy use. I mean, your brain uses less energy than an incandescent light bulb to do everything that it does. And so maybe we can finally approach the energy footprints of real biological brains. And that's what some of these hardware platforms are getting us closer to do. All right, so I'll pick up where we left off there, just talk about how these SNN architectures work. I'll give you an example of one of them and how it does unsupervised learning, and then we'll transition to the next unit. So we'll finally be done with neural networks after that. So that's all I got. You guys can get out of here. If you have any questions, I'm happy to take them now. If there's any questions online, I'm also happy to take them, but it's all my new content for today. Are there any other questions online? All right, in that case, I will stop the recording.